So let's get started. So for today's lecture, we will talk about image segmentation. So far we've kind of dive into the deep learning technique, right? So we talk about different deep learning architectures, starting from fully connected layer to CNN to recurrent neural network and also transformer architecture. And we mostly, some of the applications we talk about is focused on image classification. So now we are going to another topic, which is also very important in general computer vision, as well as medical image computing. So that is the image segmentation task. Okay. So for image segmentation, so I think there's a, you can sort of, based on the application needs or your objective, right? So you can view differently. So for example, let's say we have an image, we just wanted to discover some of the patterns, right? And group pixels into regions that may share similar properties, right? So maybe these similar properties can be, same color, same pixel intensity, and etc. Right? So this here, the superpixel-based approach is basically, grouping pixels into a superpixel, which is like a region or combination of multiple pixels, right? Maybe within each of the superpixel, they all share similar properties, right? They may be corresponding to the same object or corresponding to the same background scene, right? Here, this is another example, right? So we are not specifically grouping the pixels maybe towards the same object, but we want the pixels, they group together, share the similar properties, right? Maybe color and some other things. So you can think of this as kind of like clustering, right? So clustering is we want to cluster the data points, right? So that within each of the cluster, they share similar characteristics. So here, the data points can be considered as each pixel, right? So we group them according to some of the properties. And we can also, view image segmentation as, group pixels into meaningful objects, right? So this is object level segmentation. So we want the accurate localization and recognition of the objects, right? So as shown in this example, right? So we wanted the grouping of the pixels actually have some semantic meaning, right? So this group of pixels will correspond to a specific object, right? This may be a bicycle, right? So in this green color, and this group of pixels will correspond to another object, right? A person, and we have buildings and other semantic classes. Okay, so this is the most common when we talk about semantic segmentation. Usually, we're referring to we want to classify or segment the image into different semantic classes. So formally, for semantic segmentation, we want label every pixel in an image, right? So we want to assign a label to each of the pixel, right? So for image classification, we just want to assign a label for the entire image, right? We don't care about like a more refined label within this image for each pixel. But semantic segmentation, you can consider this is a more refined classification problem. So we want to, designate or predict a label for each of the pixel. And this is very important for scene understanding, right? So for this image, if we are able to classify or segment different objects, then give us some of a very good idea about the scene, right? So what are the objects in the image? What's their scene layout, right? Their geometric information, positional information, etc. And you can imagine this has a lot of applications, right? So here I just list a couple of very important applications. For example, the autonomous navigation, right? So for a lot of in the future, we all have self-driving cars, right? So for the cars to drive by themselves, they need to understand the semantic world, right? So where are the roads, right? Where are the pedestrians and different objects, right? So we need semantic segmentation of the scene, right? So we need to segment each of the frame in the incoming video coming from the videos. And we can also using semantic segmentation to assess the partially sighted, right? So we can using semantic segmentation maybe to help visually impaired people to understand the world and help them to navigate. And this can also be useful in medical diagnosis, right? So we can using segmentation to detect or segment tumor or different organs of the human body. And here is an example, right? So we can do this dental analysis, right? And we can also using segmentation to do image editing. So here, basically, we can segment different or parse the human body, right, into different parts and easily to do some editing, right? Maybe this is a some website selling the clothes, right? So you don't want ask the model to try every possible styles of their t-shirts, right, or dress. Maybe you just try one, then you can easily segment different. This is a t-shirt, this is a dress, and then kind of swap out a different style, right? So this make it very easy and scalable. Okay. So one thing to emphasize is that for semantic segmentation, the goal is to label every pixel, right? So recognize the class of every pixel. But sometimes the same object or same class same object with belong to the same class can appear in different regions or places in the image, right? So for this example here, so this person riding a bike, so we actually have two people in this image, right? So for semantic segmentation, we do not differentiate these two instances, right, to these two people. We all classify these pixels to the same class as the person class, okay? But there's also another a task called instance segmentation. Is you also want to distinguish the instance, right? So if there's two people or even more, we not only want to classify as the class of person, but we also want to differentiate different people in the image. Okay. So here is the kind of like a comparison, right, with semantic segmentation and the instance segmentation. Okay. So as you can see here, right, so from the label information, right, the semantic segmentation, maybe we can just look at this image, right, in the bottom. This may be more clear. So we have many birds in the scene, right? So we have a class called birds, and we also maybe have another class called bottle or maybe other objects. So here we just classify them into the corresponding semantic class. But for the instance segmentation, right, so you can view from this ground truth instance segmentation map, right? So for, there's multiple birds in the scene, right? We designate different colors for each of the instance, right? So we not only classify them as a birds class, but we also want to differentiate from each other. So this is more, you can consider it's more kind of fine-grained classification, semantic segmentation, right? Not just the class, but also want to differentiate different instance. Okay. So for since this semantic segmentation or instance segmentation is a very important task, so there are many database to evaluate segmentation. So here I list a couple of popular database so that people can use this to evaluate their algorithm and do the comparison. So this is the Pascal Visual Object Classes dataset. So it has 20 categories, about 10,000 more images. It has ground truth for semantic segmentation. Okay, so like this, right? They mixed all the instance to the same person class, and they also have the instance segmentation ground truth, right? So differentiate each of the instance. And this Pascal context is another one. So it's focused on real indoor and outdoor scenes and has more categories, has 540 categories, and also has these dense annotation for semantic segmentation. Okay. So here are also a couple of more data set. So this Sun RGBD database. So this is can consider as a multi-modality data set, not just RGB, conventional RGB image, also can have the depth image. So the depth means measure the distance between the camera, right? So show up in the on the depth map. Okay. And this COCO common objects in context is also a popular database. So it actually has served as a multi-purpose database. So you've heard of using COCO for object detection, right? So COCO can also be used for segmentation and instance segmentation. Okay. And we also have this cityscape. So this is kind of created for autonomous driving or understanding the street scenes. So it contains the real driving scenes, right? So basically, the cars go through different cities and the streets, right? So they mainly have those categories that may be commonly seen on the street, right? The buildings, trees, pedestrians, right? Roads, or maybe other traffic signs, etc. Okay. So you can also have the semantic segmentation. You can also do instance segmentation. Okay, and there's also another one called ADE20K. So these are the common data set people are used for evaluation for the task of semantic segmentation or instance segmentation. Okay. So now you kind of have a initial idea, right? So what is the semantic segmentation, right? So what are the data set available if you are interested in doing some experiment or doing some application for, using semantic segmentation? Now comes to the question, right? So how can we do semantic segmentation? So far we understand a lot from image classification, right? So we can build a network like CNN or RNN or transformer architectures to extract features. And we have this fully connected layer and softmax to output the probability for each of the class, right? So if you have 100 classes, for classification, then your output will be a 100 dimensional vector, right? Indicating those probability for each of the class. So, but that is just a single output vector, right, for the entire image. Now the task become more complex, right? So we are not interested in the whole image. We are actually interested in individual pixels in that image. So how do we go from classification to semantic segmentation? So how can we achieve that? So before I jump into some of the common solutions, I want to think about this, and hopefully if you have any thoughts, please feel free to share. Straightforward or simple method to do semantic segmentation, right? So fundamentally, there is nothing different for semantic segmentation as compared to classification, right? So more or less, it's just doing classification. So in this case, what we can do is let's just take the unit, right? So for image classification, the basic unit is this entire image, but for semantic segmentation, we are dealing with pixels, right? So the straightforward is, okay, let's just take the unit input, which is the pixel, and maybe we can apply the usual classification network, right, to generate the corresponding label for that pixel. But in this case, you are only consider one pixel, right? So it's impossible to classify it, at least classify it correctly without any context, right? So you only know, machine only see the pixel value like numbers, right? Just one number if you consider it just a grayscale, right? You just have a single number. And it's very difficult or challenging for the machine learning algorithm to figure out, right, which class it belongs to, right? Maybe, there's highly possible, right? So there's two pixels maybe corresponding to different classes, but they share or they even have the same, pixel intensity, right? So without the context, it's very difficult to classify each pixel correctly. So then we can say that maybe we can inject some of the context, right? As Nashar just mentioned, right? Maybe we can take a small patch, right? So that give us some of the context, right? So what we do is maybe we can, if we want to classify a pixel, right? So we take that as the center, and we use that as center, and then we crop out a small patch, right? So in this case, we have some context around the center pixel. So this patch could be, just to, for example, we can have like 10 by 10, or if you have more context, we can have like, 30 by 30, 50 by 50, right? So the patch size can be adjusted or optimized, right, based on the performance. So in this case, we can we can set a sliding window, right, which determine the patch size, 30 by 30. Then we slide across at each pixel location, right? So we slide across this entire image, and we can still do this as an image classification problem, right? In this case, we just take a tiny or low resolution image, right, as a patch, and classify it and set the label for that center pixel. So that's the straightforward way we can do. But the problem is that it's very inefficient, right? So we have to do this repeatedly, do this process classification for literally every pixel location, right? So you can imagine how many, if we're talking about inference, right, how many forward passes we have to run in order to generate a segmentation map for the entire image, right? So if we have a high resolution image, like 4K by 4K, right, you can imagine how many forward passes we have to run in order to generate this 4K by 4K segmentation map. And also, we are not to reuse shared features between overlapping patches. So another way we can do is that, so if we are not consider, this classify each of the small patch is not efficient, right? Maybe we can, go for another option, that is we design a network with only convolutional layers, right? For the classic CNN network, we have this pooling operation, right? So to reduce the size, and for one thing is we can increase the receptive field size, and on the other hand is we can reduce the complexity of the network, right? Because you are gradually reduce the feature map size, so the number of operations can be smaller. But that's for classification, right? Because after all, we only care about output vector as the label probability for the input image. But here, the desired output is going to be a segmentation map, right, which has the same size as your input, right? So here, the spatial dimension of the input image may be 200 by 200, right? So the desired output for your prediction should also be 200 by 200 segmentation map, right? Each of the pixel indicating a class for one pixel. So if we're using the pooling to reduce the size, maybe you're not able to generate a segmentation map of the same size. So the simple way to do is that let's just remove the pooling, right? Let's just only keep the convolutional layer so that we always keep the full resolution, right, as the original input, and we extract features, and at the end we generate. Let's say here we have a 10 classes. Okay, so we generate like a H times W times 10 feature map, right? So each pixel location is 1 by 1 by 10, right, dimensional vector, and this can still be interpreted as the probability, right, for each of the class. But the problem here is that convolution at the original image resolution will be also very expensive, right? Because you're always gonna operate at the full resolution at every conv layer. So if you have a very deep network, right, so you can imagine how many parameters you have to optimize for the entire network. So this is very expensive to optimize. So to kind of mitigate this issue, right? So this paper here, they are using a classification network and trying to adapt it to the fully convolutional network. So basically, what they do is that, you know, if you look at the architecture here, right? So this is like a standard CAN for classification, right? So you have the conv layer you're pulling, right? So the size of the feature gradually decrease, right? So these are the number of filters or feature maps in each of the layer, and eventually you get, you know, for this example, it has, you know, this Pascal data set has 20 classes, and then consider another class as background, so we have a total of 21, right? So you have a reduced spatial resolution with a channel size of 21, indicating how many classes for this particular data set. So what they do is that, you know, because we need to have a segmentation map has the original size, right? So in this case, they do the bilinear interpolation, right? So you just directly doing the interpolation from this low spatial resolution to the original spatial resolution. Okay, so in this case, the computation complexity can be reduced because you still gradually reduce the spatial resolution. But just in the end, you're just using the interpolation to kind of increase the resolution of your predicted classification map. Okay. So that's one solution you can do. Another way is, which is, this is kind of like a default or de facto framework now for this semantic segmentation. This is the encoder-decoder structure. So the encoder is nothing but just like a CN, a CN network, right? So you have the normal conv layer, pooling layer, and, you know, maybe batch norm, some nonlinear activation layer. So these are the pretty standard operation, right? So you gradually encode the features into the high-level representation, right? You also reduce the spatial resolution for efficiency, and also trying to aggregate more context, you know, for within this feature map or from the original input. And because, as we mentioned, right, so the ultimate goal is we generate a segmentation map have the same size, right? So that's the responsibility for the decoder, right? So basically, it's kind of doing the reverse, right? So if you look at the structure, right, it's kind of symmetric, right? You have the encoder side, right, which is have this, you know, on the left, right, blue and the green here. But on the right side, this is a decoder, right? So you're gradually upsampling your feature map to the original size, right? So you from the beginning here, smaller spatial resolution, then you do the upsampling, right? So, you know, if you always do the, you know, pooling, reduce the spatial size by half, you know, every time, then you can do this symmetrically, right? On the decoder side, you can always upsample the image, double the size every time, right? And then gradually you come up with the feature map of the same size, then you can generate the semantic segmentation map. Okay, so this is the encoder and the decoder structure for semantic segmentation, which become a standard framework or pipeline for this particular task.